Let's take a look at how to tackle a regression a regression question using Google Sheets/Excel. So here's a typical question. They give us the weight of cars in pounds and then the corresponding mileage in miles per gallon of all those vehicles. And we're going to run some regression on this. So the first thing we can do is copy our data and paste it into Excel. Now I have my Google Sheet set up where as long as my X values are put in A and my Y values are put in B, everything's going to kind of auto-populate. And you can see that these numbers all adjusted. So the first one is the simple count function, right, where it's just counting up how many numbers I have in column B. I could have just easily done how many numbers I have in column A, because when you're doing n sample size, it's number of pairs, right? And since they're going to be paired up, you're going to have the same amount of numbers in both column A and column B. Okay, we need to know the minimum and the maximum of our X values, the input, right? The sometimes called independent, sometimes called explanatory variable, basically the X, right? The thing that is kind of influencing the other thing. So in this case, the weight of the car influences its miles per gallon. So that's our input. That's our X, is the weight of the car. And we need to know the minimum value of the weight. And we also need to know the maximum value of the weight. This will come up here in a second when we talk about that. Then I calculated the correlation coefficient R, which is very simple with the choral function. The one thing with the choral function that you have to realize is that they want the y values first and then the x values. See how it says data y, then data x? So you have to tell it to take the column where the y values are first and then the column where the x values are. So that's just kind of a weird thing where it's backwards. This is r squared, our coefficient of determination, which of course I'm literally just taking the square above it, the cell above it, and squaring it. And then here I had to do a little a formulation where we're recreating this lovely formula for our test statistic, our t value. And you can see it's pretty straightforward, right? We've got f4, because that's where my r is, divided by the square root and everything inside the square root. And then you just have to realize that you have to put parentheses around this and parentheses around that, because you need this whole number divided by this whole number. So that's why I've got 1 minus f5, because that's where my r squared is, and then divided by f1 minus 2, because f1 is my sample size. And so the n minus 2 becomes the degrees of freedom for this kind of test. That gives us a t. Then we can run our p-value, which is the t-dot distribution function. And when you have the t-dot distribution function, it's always going to take the area to the left of it. And because we don't know if our t value is going to be positive or negative, we have to take the absolute value of our t. So that's why I've got the absolute value of f6. So it's taking this and it's turning it into a positive 15. So now any kind of t I get, whether it's positive or negative, I'll always just get the positive version. Then I'm going to take the t distribution of that and then do 1 minus it, right? Because when we have positive t's, we're looking for the area above. But if we do the t-dot distribution function, it gives us area below to the left. So that's why we're doing the whole 1 minus thing. We've done this same kind of computation in our other calculators where we were calculating p-values for other things. And then the second thing it wants is degrees of freedom, which is this minus 2, right? And then the true is what gives us that accumulative area, everything to the left of it. Okay, the next two are the actual pieces of our linear regression formula. We're going to come up with the equation of a straight line, good old y equals mx plus b, right? In this case, it's y hat, because we're predicting y, so y hat just means a predicted y, kind of a guesstimated y. And that mx plus b, the m, the slope, we can get from the slope function. And just like the correlation function, you put in the y column first and then the x column. So that's why it's the BB comma AA, right? Because you're doing where the y's are sitting and then where the x's are sitting. And then the same thing for the intercept. It's the intercept function, and again, the b column first, and then the a column. So that's my m and my b, right? Slope and intercept for my equation, if I wanted to write out the equation of this straight line. And then this down here I have set up for doing some work that we're going to do further on in this question. So let's go back to the question and answer some bits and pieces. First thing it wants us to do is state the random variable. Well, that's pretty easy, right? It's going to be the weight of a randomly selected car, because that's the x, and then the y is just the mileage of a randomly selected car. Then it asks us to actually compute some things, right? We need to find the equation of the best fitting line, i.e. the regression equation. Here's that y hat, right? We need y hat because we're estimating our y. And then they write it kind of weird sometimes. You got to pay attention. See how it's something plus something times x? So this is our slope. The second box is our slope because that's our mx plus b. They're just writing it as b plus mx. We all know that's the same line. Why do they write it one way versus the other? Just to confuse you. No, it's just kind of a standard thing that's happened in statistics. But anyhow, we need the slope in this box, the intercept in that box, and they want it to 3 decimal places. Let's go back here. Let's change both of these to 3 decimal places. So now we can get this one, and I know the other one is negative 0.009. So my intercept here and negative 0.009. And if we check it, same numbers. Now, the restricted domain. This is when I was talking about where we need to find those minimums and maximums for our x values. So we've got a minimum of 2250 and a maximum of 5500. So this is 2250 and 5500. The reason being is we are only allowed to make these predictions to try and predict what a y value would be for x values that are within the range of data that we've observed. Because we don't know if the pattern that we're creating with this straight line actually holds outside of this sample. So we don't have any cars that are less than 2,250 pounds, and we don't have any cars that are over 5,500 pounds. We found this nice little, linear function, this y equals mx plus b, that seems to fit our data fairly well, because if we look at our results, we've got a really strong r, right? 0.97 and then a 0.94 for r squared. This is a great model. This is really doing a great job of predicting these values, but it's only as good as the data we give it. So it's only really good at predicting this set of data in this range of numbers. If we put a car in there that weighs a lot less, so 1,000 pounds or something, a super light car, we don't know if this trend is going to hold. I mean, obviously it should get better gas mileage, right? It should go up. But is it going to go up at the same rate that these are? Because remember, we have a linear function, so we have a straight line happening here. So basically, we just can't do any kind of estimations outside of the range of the values for x that we actually see within our sample. So because we only looked at cars that ranged from 2,250 up to 5,500 pounds, we're limited in only being able to predict miles per gallon for cars within that range of weights. Okay, now we can interpret the slope and the intercept. Well, the slope of any line is the rate of change. It's how fast the y value is changing every time the x value changes by 1 unit. So every time we increase the weight, because that's the x value, by 1 pound, because these things were in pounds, right? So we go up by 1 unit. We can expect the y, right? So the mileage now because this is negative, it's going to decrease by this much, right? So that's why it's just 0.009. And what are its units of measure? Miles per gallon. That's what the slope tells us, is every time we raise the weight of a car by 1 pound, it's going to lose 0.009 of a miles per gallon thing, right? And then the y-intercept, right? The y-intercept for a straight line always means the exact same thing. When x equals 0, this is the value we get for y. So when the weight is 0 pounds, we expect y, the mileage, to be this 59.604 miles per gallon. Now, does it make sense to interpret the y-intercept in this problem? No, not at all. First of all, it doesn't make sense to have a car that only weighs 0 pounds. But more specifically, it doesn't make sense because x equals 0 is not between the minimum and maximum. It's not within our restricted domain, so we really can't do any kind of quote-unquote predicting of what would happen with that as a random variable. Okay, how about 2727? Could we make a prediction for the miles per gallon for a car that weighed 2,727 pounds? Well, yes, we could. And we can do that because that value is between the minimum and the maximum, right? The minimum was 2250 and 5500. So it sits in there. So we could predict on that. But what about 8079? No, we can't predict that because that's outside of our range. It's, too big. It's beyond the 5500. Okay, so now we know between these two options, 2727 is the one that we can use. So we can use a weight of 2,272 pounds and we can predict the mileage. Well, how do we do that? We have to use these bits and pieces and create an equation that's going to predict it. So the x value we had was 2727. And the predicted y value, well, y is going to equal m, our slope, times x, the x value we put in, plus b. We're just doing y equals mx plus b. And there is my predicted 35,334. And here you can see 35,334. And then, of course, the unit of measure is miles per gallon. So we could predict that a car that weighed 2,727 pounds would get a little over 35 miles per gallon. Okay? This next piece asks us to kind of predict all over again, but with a completely different piece of data. So 2727 is done with. We predicted that one. Now we're going to move on. And now we notice that within our data set, we had this car. We had a 3,000-pound car with a 31.4 miles per gallon. If you go back up here, you can find it. There's 3,031.4. So we actually observed that. We saw that happen in real life. We have that data. Now we can calculate the residual. And the residual is basically the mistake that we get from our predicted amount. So let's go back to our calculator. We have a 3,000-pound car, and we observed that a 3,000-pound car had 31.4 miles per gallon. So that's the observed y, 31.4 miles per gallon. The predicted y is 32.94. See, because the way I set this up, it just takes whatever I put here as my x, right? So it does slope times x plus b, and it gives me my new prediction. So my new prediction is almost 33 miles per gallon. Now we have to figure out the residual. Now over here, it says the residual is, well, negative 1.5. Where does that come from? Well, remember, the residual is the difference. And the difference is always calculated as the observed, the actual one that we have in our data set, minus the predicted. So it's simple enough. It's just going to equal observed minus predicted. And there's where we get the negative 1.504. So the residual is negative 1.504 miles per gallon, because again, this is the unit of measure for the y variable. And because the residual is negative 1.504, that tells us that the actual mileage of a car that weighs 3,000 pounds is going to be 1.504 miles per gallon below what was predicted, right? Because the negative tells us below. And if you go back and look at this, we predict almost 33, right? But the actual was 31.4. There's that 1.5, right? That it's lower than what is predicted. And that's pretty much everything we need to know for regression. It's pretty simple if we just use these kind of simple little functions in Google Sheets. The only thing we have to really do is compute our t-value for if we're going to do the kind of the hypothesis test portion of these types of questions, which we didn't see in this one, but we've seen in other examples. All right, hope this helps.